all right. Up until now, we spent a lot of time developing techniques for analyzing circuit, but with an eye on design. And the way we did it with an eye on the design was basically by producing analysis techniques that are not just blind application of KCL and KVL. Rather, they allow you to understand what affects what and create some sort of a causal relationship between the parameters. So today, we are going to talk about slightly different viewpoint that again also can be done what we'll do will be a very design-oriented approach, which is the feedback viewpoint. We call it feedback viewpoint. And there's a reason we call it a viewpoint. Because if you think about what we've done, any circuit that you have right now, you should be able to analyze from low and high frequency perspective, right? I mean, you could analyze it all the time. I mean, always, if you had linearized it, you can always do nodal analysis, for example. But then we've developed more advanced techniques, which basically allow us to kind of break down the transfer function and high frequency behavior of the circuit into this time constant and transfer constants and all those things. So if our only goal was to do analysis, there would be no need for additional techniques, right? We can analyze everything and anything right now. So we will develop a lot more additional techniques, and the purpose of these techniques is really design. So they are useful to the extent that help you with the design. Now, feedback is in fact I would say one of the top 10 engineering tools ever created, probably even like top 5. I would call it, top 1. That's debatable. But yes, feedback is a very powerful tool. And like any other powerful tool, if you use it properly, you will get good results. If you don't use it properly, you will not get results. You will get surprising results, in fact. And we'll talk about some of those things when we talk about stability issues and all those things. But right now, we are trying to understand feedback. Now, the primary purpose of the tools and techniques we develop in the next few lectures is to give you a quick and understandable and intuitive way of designing feedback networks and circuits using feedback. Okay? So we'll write things in a way that allows us to decouple things, different effects from each other. The same way that we try to do with the time constants. Okay, so much talking. So let me just give you the key ingredients of this thing. So what is feedback? Now, there are different ways to think about feedback. In system analysis, there are, when you have boxes that have input and output, and these inputs and outputs don't have really impedances. You just take a branch off of the output and feed it back to a difference or a sum, and then create a feedback network, right? So in that picture, a lot of times what you draw is something like this. You can say, okay, I have an input, I have a difference point, and I have some feedback. So I have an input X, output Y, there's a forward dynamics, and there's a feedback network and something like that. This picture is useful if you are really treating these things as signals that do not get loaded or things of that sort. Now, when you're dealing with circuits, you have to be a little bit more sophisticated than this. I mean, you can try to do this, and you can try to force this onto the circuit network, but then it will generate all sorts of these like funny two-ports that we will see some of it when we try to kind of like prove some of the things that we are trying to do. We don't use it regularly as a design tool, but when we try to prove some of the results or things like that, so we may see these like you reduce this to a 2-port, and then this 2-port, and then this is loading that 2-port, and things of that sort. And that's kind of like a more traditional way of doing it. I don't think that's the best way of doing it. So we'll change this viewpoint. We don't use this viewpoint. Actually, we draw this slightly differently to capture the fact that these are circuits. How do we draw it? So there's a forward amplifier generally, and this amplifier, there are two inputs to it, what we call UI plus and UI minus. Now, we show them as U's because they can be currents or voltages. So a U in general is and there's a UO, and UO is A times UI plus minus UI minus. So there's some A, and in general, this A can have dynamics. We'll see later, it can be even nonlinear, and then we'll see what happens when these things happen. And then we take this UO, and then we have another network, which is really a circuit, and providing and producing this UI. Now, the way we are drawing it right now, there's an implicit assumption of unilaterality. What do we mean by unilaterality? Meaning that signal flows only in one direction here, in the forward direction from left to right on the A, and from right to left for the F. We'll go back later, after we develop the basic techniques, we'll go back and revisit the bilateral circuit system and see how it changes things. So we'll talk about that later. But first we have to do the first order things, clearly. Okay, so, and this is the UI, right? So this is the input to the circuit, and this is the output to the circuit. Again, you may say, what's the big difference? This looks the same thing as that. Well, we'll see what the difference is a little bit. So what is the transfer function? In other words, what is h, which is defined as y over x? How do we determine that? So this is what we're trying to determine. Well, we notice one thing. We use this relationship, right? So we know x minus ui minus, which is this difference, right, times a is uo, which is y. So we can say, let me write it this way. Y equals uo equals a times ui plus minus ui minus. But ui plus is x. And what is ui minus? If this is a unilateral thing feeding it only back. F times y. So for now, so far, at this point in analysis, we assume that f is a scalar, meaning it's just a constant multiplying by. We'll change. We'll see what happens if it has dynamics. We'll see what happens when it's nonlinear, things of that sort. We'll talk about all of those in detail. But for now, let's assume it's scalar. So, I mean, this is a very simple equation. You can easily solve it to get what h is. And when you do that, you will get the result that probably most of you are familiar with. You get some a over 1 plus af for the transfer function with the feedback. Okay? So nothing out of the ordinary. You say, OK, well, you got the same result. What's the big deal? Now we introduce a parameter which is the most important parameter in feedback circuits. The single most important parameter, bar none, which is what we call asymptotic transfer function. And we show it with h sub infinity. Now, there is a little bit of a, it's not really, but there looks like a little bit of an notation overload here. Because, you know, you remember when we were talking about the infinite value time constant, we put an infinity, but that infinity was in the superscript, and this infinity is in the subscript. So it really is not a notation overload. So not to be confused with that, has nothing to do with it. Okay? H infinity. Now, what is H infinity? The asymptotic transfer function is defined as h when you actually put a scaling factor k here. So you take one of the parameters, let's say this gain, and in general we'll look at the transistor parameters, for example, and we look at one of those sources, preferably the one closest to where this summation or difference is happening, and define this parameter k, lowercase k, and then we say it's h when k goes to infinity. This is the most important parameter in feedback. This is the useful part of feedback. All the other parameters that we will develop after this are parasitics, are things that are non-idealities, or to account for deviations from this ideal behavior. This is the ideal behavior. And we'll see that. I mean, I haven't shown it to you yet, but I'm going to emphasize it now. Now, let's see what happens if we do this in this equation, right? So A becomes Ka, so you get Ka over 1 plus Kaf when K is going to infinity, right? And you can clearly see what is this result. What is this? 1 over F. So it happens to be 1 over f. It becomes 1 over f. And the interesting thing is that it says that it's independent of a. So this parameter is independent of a. Now, this is slightly different from saying a is infinity or a is very large, which we'll do. When you say, and you remember when we were developing like these amplifying stages, we were on this like seemingly meaningless quest for more and more gain, right? Now, of course, you can see if you can make a very large, this does reduce to 1 over f. That is real. I mean, so that's what happens in reality. If you have a large a, then your gain is really determined by the feedback network, right? This is true even if a is not infinity. This is the ideal, this is an ideal image of what the system would look like if the gain were infinity. And we'll see how they kind of like create a little bit of a that differentiation may matter. But so the idea here is that this is what the feedback loop should look ideally, or what the feedback loop does, the transfer function looks like ideally, even if a is not infinity. Then there will be correction factors to this. This is what you design to. And when I show you circuit examples, you will see what I mean by what you design to. So basically, you say, I want my feedback network. You say, I'm making a circuit. I'm trying to achieve this behavior. I'm using feedback here. And I'm trying to get a gain of 10. You try to set your H infinity, which is relatively easy to calculate generally if you do it the right way, to 10. And your circuit will have a gain close to 10, unless you just have no gain. And then there are these correction factors to it that we'll introduce that makes it more accurate. If you need to calculate it more accurately, you want to see how much it deviates from that ideal thing. But this is the design tool. OK. Now, if you think about this, then it leads to a principle, which is what I call an asymptotic equality principle. OK? What is asymptotic equality principle? So asymptotic equality principle says that when in the presence of negative feedback, so let's say, first of all, one of the things is that there are really two kinds of feedback. One is positive feedback, one is negative feedback. And the difference is, one reinforces, so let's say, how do we know if it's positive or negative feedback? So let's say these are the polarities, right? So if this node goes up, this goes up, let's say this doesn't change polarity, this node goes up, and this goes up, but because of this minus sign, this pushes this node down. So in this arrangement, assuming f is positive and a is positive, then you have a negative feedback. Now, you could also have positive feedback where when you come back, you're in the same going in the same direction, and you can increase what's happening. In fact, positive feedback was used first and was introduced first. The way, and you have already seen positive feedback, by the way, in some of the circuits we've looked at, both in lectures and problem sets. The negative resistance, the cross-couple thing, that's positive feedback, because one side goes up, the other side goes down. When it goes farther down, the other side goes more up. It's basically a latch, if you think about it that way, right? But negative feedback was actually invented later. It was invented, I think, in 1936. There's a patent by Harold Black that kind of like describes it. And it was invented for a reason that we'll discuss a little bit later. So what does asymptotic equality say? It said, look, if the gain was infinity, if k goes to infinity, there's one, and if this system is negative feedback, then it means that you have a finite, the negative feedback will guarantee that you have a finite value at the output. It's not going to go to infinity or positive infinity or negative infinity. So if I have a finite output here with infinite gain, what does it tell you about these two inputs? What's the only way? Because remember, this gain, well, now it has become Ka, right? Times this difference produces this finite output. So you have an infinity times something producing finite. What is that something? Zero. So these two have to be equal asymptotically. And that's what asymptotic equality principle means. Means that once you identify these ui plus and ui minus, they would be equal when you calculate h infinity. And that's basically the way you calculate h infinity. So, well, they are going to be equal when k goes to infinity, when it's very large, right? So, and a special form of that is something that you may be familiar. This is like, they call it the virtual ground, kind of like in an op-amp when you have negative, basically just the input. It's when one of the positive terminal is shorted to ground and the negative one is kind of like saying, oh, it's going to be at virtual ground. It's a very special case of this general asymptotic equality principle, which we'll see both in op-amps and in a lot of actually transistor level circuits. So that's a little bit in the way of background. I just want to kind of make sure that we are on the same page. So let's do an example for you guys to, we'll do a bunch of examples. So as we are introducing these things, we'll do a lot of examples as we go for you to develop a sense of what we're talking about. So let's do our first example. Let's make our first example not too complicated. Let's make it an op-amp, okay, in the non-inverting configuration. So you have a resistive divider here. You still have to have negative feedback. So this path, this needs to be connected to a negative. So this is your V in, and this is your V out. This is something everyone is familiar with. We want to just see how we do it if we apply this method exactly. And this one is R1 and R2. So what we do is that first we set the K. We put a K here, right? And then we can basically call this, I don't know, Vi plus. So this is basically, now Ui is Vi. So this is Vi plus and this is Vi minus. Okay, so what do we know? Let's say if K goes to infinity, then these two have to be equal or asymptotically equal. Asymptotically equal. You know what? I'm just going to abbreviate it. Asymptotically equal. Okay? And if they're asymptotically equal, what do we know? Well, then it means that the feedback loop will force the output in such a way that this voltage, which is this voltage, is equal to that voltage. Which basically means that this voltage has to be V in. Right? But what is the relationship between this voltage and that voltage? Well, it's a voltage divider. We know V out times the division ratio, R1 over R1 plus R2, is simply V in, if when K is going to infinity. So V out over V in, which is H infinity, in this case, is going to be 1 plus R2 over R1. So that's our H infinity, right? And if somebody says, okay, well, I want to map it to that picture of that box F in the feedback path. What is F? Well, we know F is 1 over H infinity. So if you really insist on, I'm trying to stay away from F, actually. But if you want to kind of like know what F is, sometimes we want to know it, so it's going to be R1 over R1 plus R2. Which in this case makes perfect sense, right? If you think about this as the feed, this is a simple enough one that are idealized. The output is ideal voltage source. The input is like an ideal voltmeter. And yeah, it's a resistive divider. So that's the ratio of the resistive divider, R1 over R1 plus R2, which is exactly what we see. So that's your feedback network if you want to kind of break it up. And we are trying to not to break it up for now. You actually want to try to kind of develop a method that does not require you to break the loop. And then we'll see that there's a full method based on that. And then we'll see if you really want to break the loop, what's the correct way of breaking the loop when we talk about loop gain. Okay, so what is this, by the way? What do we call this? What are we doing? Because we said these parameters could be voltages and currents, right? So there are two different naming conventions, and they're sufficiently confusing in the sense that they've made it that they're different in various ways. And some people use them both. So I'm going to talk about, because you will hear these names, I put them also kind of in the handouts so you're familiar with them. It's important to understand it. And the point where they matter is really when we talk about impedances. Yes?
In your example above, are you also assuming
I'm assuming
infinite
infinite input impedance. Yes.
Is that like given by like your other like
At this point, no, it's not. But you will see that a lot of times, actually, when you use asymptotic equality, you don't even need to assume the input impedance when we get to the transistor level. So that's a great question. And I'll try to kind of point it out when we get to the other example. But that's a good question. But in this case, I'm just assuming it to make it simple. This is a very simple example. We'll do a lot more sophisticated examples, in effect, in a few minutes. But let's talk about naming convention here. So there are two things, right? So there is how you do this subtraction, because this is still abstract, right? How do you do this? It's really, subtraction is an addition, right, with the different signs. So how do you do this addition is a function of whether or not this is what they are. Are they voltages or currents? And how you sense this output and feed it back is also a function of what kind of like voltage or current you have, right? So there are two conventions. So one of them, which is the one we will be using most of the time, is defining the way the input and output are connected, starting with the input. So, for example, if you have two currents, if you want to add or subtract two currents, what do? You put them in parallel or in series? Two current sources. When you add two currents, you put them in parallel, right? You put them in shunt, right? So you have the input connection, which can be shunt or series. So this is the input and the output connection. This is describing the connection. So shunt, for example, means in parallel. So and then you will have multiple variations. So you will have a shunt. You can have a shunt, and then when you measure a voltage, what do? Or if you're measuring a current, for example, when you're measuring a voltage, how do you connect your voltmeter? Do you connect it in parallel or do you connect it in series? Do you put it in series, the voltmeter? You put it in parallel, right? For a voltmeter, because a high impedance thing. If you put it in series, no current will flow. So, and I will tell you what they mean in terms of what they say. Shunt, so they can have shunt series, obviously it's the four combinations, right? Series, shunt, and then series, right? So that's one convention. There's another convention, just to muddy the water more, that people sometimes use, which is the convention of sense and return. What is the quantity that you're sensing and what's the quantity that you're returning? Now, remember, even the order is flipped now, because you sense at the output and you return to the input. So what is here corresponds to output, and what is first in this convention corresponds to what's second in this convention, and what's second in this convention corresponds to what's first here. It's very confusing. I think this is unnecessary, and we are not going to be using it, but you will see it, so I want to make sure that you are familiar with it quickly. So now, let's try to see one-to-one correspondence. If my output is shunt, what am I sensing? What do you sense in parallel? A voltage or a current? Voltage. So this is voltage. And if you are feeding back in shunt, meaning that you're putting two things to add them in shunt, in parallel, what are those quantities? Current. So this is a voltage current feedback. Now, this is the same. So if you're still shunt, it's still voltage. So that doesn't change. Now, of course, we're going to series. You're returning two things in series. You're adding two things in series, which basically means that they're voltage sources. They're voltages, right? So this becomes...
I think I forgot to flip them. Yeah.
Sorry?
The first one's current.
Oh, yes. Well, yes, correct. Yes, thank you. I forgot to flip them. Right? I got confused by it. You're right. So if the output is series, I'm measuring something in series. My meter is placed in series. It's an ammeter. So it's a current. Thank you for pointing it out. So it's current. And of course, I'm returning in shunt, which means that I'm adding two quantities in parallel, which means that they're current sources. So it's current. And then, now, if I'm going to shunt at the output, series shunt, meaning the output is shunt, basically I'm measuring a voltage and returning a what? a voltage, because they're added or subtracted in series. And again, if it's in series at the output, meaning that I measure a current, and I'm in series at the input, I'm returning a voltage. Right? So there's this correspondence. I think this is a better way to think about it, because one of the main reasons that you think about this, most of the times, is impedances. You care about the configuration when you care about your input and output impedances. And this allows you to see, first order, what happens to the input and output impedance right there. You can see that if something is happening shunt at the input, meaning it's lowering the input impedance, because you put something in parallel with what you have, it lowers its impedance. And if you put something in series at the output, it's going to, or at the input or the output, it increases the impedance. So right by looking at this, you can see what's happening to your impedances. So we will stay with this convention, know that this convention exists. So sometimes we say, well, what are we sensing, what are we measuring? There's a one-to-one correspondence. It doesn't have to be this complicated, really. So the way they are connected. So based on that discussion, what configuration are we in this example, let's say? So let's say go from the connection. We are doing what? Dealing with what? Voltages, right? So we are putting them, so we put a voltage and put it in series with the other voltage, right? So we are series, and then we are measuring a voltage, so we are in shunt. So we are series shunt. If I ask you what is the configuration. It only matters as far as the impedances are concerned. Otherwise, it's just a name. And we will not make a massive emphasis on this until we get to the impedance discussions and Blackman formula and things of that sort. OK, so that's for that. Again, a lot of conventions and things of that sort. So let's do a transistor level problem. Let's do another example. So this was example 1. Let's see how it works out. So on example 2, let's say you have a circuit that looks like this. So this is a resistor, goes to a PFET common source. Okay. Then there's a resistive divider. Put it here. This is V out. This is V in. And so which one's R1, R2, R3? OK, yeah. So this is M1. This is R2, R1, and R3, and M2. Basically, we have 2 transistors. And we have provided some feedback to this transistor through here. OK, so we want to understand what's happening here. And so for this one, for the first few ones, we'll just do a little bit of I'll draw the small signal model so we can actually see what's happening, and then we'll kind of stop doing it because we will do it in our heads. But let's just do the small signal model to see how it works. So let's see. So here, you don't have a source that's grounded, AC grounded, so I use the T model. So here, you use the T model. So I have IS1. This is RM1. This is IS1 going to R3. And then this guy has a source that's grounded. So I'm using the pi model for that. So since it's a MOSFET, if this is the voltage, whatever, V2, this is going to be GM2 V2 to ground. And then going to a resistive divider, R2 and R1, fed back here, and this is my V out. I'm ignoring RO, which is fine for now. So this is our circuit. You can actually, if you are, you can call this also VGS2, but so this is V2. So let's look at this and see what asymptotic equality tells us, what we can see from looking at this. What is the thing? So if you have to find a parameter, we have to find a source, we have to define something, and you ideally want to kind of like, preferably you want to pick something that's close to the inner loop and closer to your input, because it makes your equations simpler in general when you do that. When you look at the big thing, it's not necessary. You will get the correct result when we do, no matter which one you pick. If you do the 2 subsequent correction factors, which we haven't talked about. But as a kind of like rule of thumb, let's start assuming start with something that's close to this. So what should I pick to modify and scale by k? Because I need to kind of like calculate asymptote. I want to find what ideally this circuit, if this was using ideal forward path, what would it do? Where should I put my k in your mind, in your opinion? Where should the k go? What should I scale by k? The first transistor. More specifically, I take a current source and scale. Remember, I'm not scaling a parameter. So it's not that I'm scaling a GM. I'm scaling a source. So I can take this source. So it means that if I put a k here, I don't have to put a k here or divide by k here. If I put a k around in front of this GM, I don't need to make every time I see a GM2, k GM2. I'm just scaling that source, and this is important in the way you calculate this thing, okay? So I'm putting a k here, and I'm saying this k is going to infinity. So let's see if that k goes to infinity, what happens. So if that k first of all, the first thing I needed to do, which I forgot to do, is to check the sign of feedback, to see if it's negative feedback, right? So let's pick some value, right? So let's say this node goes up, this is the voltage divider goes up. So this is from the perspective of this node is a common source, right? Because this source is null, it's grounded. So this is going to be non-inverting, so this is going to go up. But this is an inverting stage. This is a common source, so this is going to push this down. So this feedback is negative feedback. So k going to infinity with negative feedback having finite output, meaning that if this is finite, means that V2 is finite. If V2 is finite with a current source that's infinity times some current, that current has to be 0. So this implies that IS1 is 0. Well, it's not going to, it is 0. Right? And if IS1 is 0, what is this voltage? The voltage between these 2 points. If the current through that resistor is 0, the voltage is 0 too, right? So these two are asymptotically equal. So this voltage is 0. Now, if this voltage is 0, then everything becomes very simple. So this is V in and this is V out. What can you say about the relationship between V in and V out? Again, it's a voltage, the same, it kind of almost looks exactly like that, right? It's a voltage divider. So we know, we can write the equation again, we know that V in is going to be V out times R1 over R1 plus R2. Therefore, H infinity, which is H when k goes to infinity, is 1 plus R2 over R1. So if I'm designing the circuit and we have a 10-second design exercise, meaning that you have 10 seconds to pick a value for these, like the feedback resistors, what would you pick? Let's say if I say you need a gain of 10, and you have 10 seconds, right? R2 and R1. Pick them. Say again? 9K, 1K, right? Or 900, 100 probably. But it depends on what current you want to set this through this guy, how much current you want to pass and how much DC you have, right? So if you're passing 1 milliamp and you have like a couple of volts, you probably 9K, 1K is going to be probably too high because you get total of 10K, and if it's 1 milliamp through 10K, that means that's 10 volts of drop. So, I mean, it's a 9-to-1 ratio. That's it. I mean, so that's your design. I mean, that's part of your design. That's the benefit of feedback. If it was more difficult, it's useless. Or not very useful in general. So that's what it is, right? That's what this H infinity does. It makes it very simple. So we'll do more examples. Let's do more examples for you to see what's happening. And then what we'll do later, when we introduce our correction factors, we'll come back to these exact circuits and calculate the correction factors. So we'll say, how far off were we from this calculation exact, from this H infinity? Yes? I see. In this particular circuit or in general? Okay, in this particular circuit. So let's assume, so let's get rid of these. You take one point in the loop and just assume that it has a small upward movement. Let's say somehow like there's a fluctuation if it goes up. Well, if this node goes up, this resistive divider will have, this node on the resistive divider will also go up, will go up less, but it will go in the same direction. And now if this goes up, if there's no input here, basically if it's a voltage source, this is going to be grounded from an AC perspective, right? So what kind of stage do we have here? It's a common gate, right? Because the gate is grounded. The input is applied to the source, it's taken out of the drain. It's a common gate. So let's say inverting or non-inverting stage. It's a non-inverting stage, right? Common gate. So basically this going up, this will go up. Now if this node, which is the same node, goes up, now remember, this is a common source. So that's an inverting stage, right? So that from an AC perspective, that flips the sign, and then it pushes it down. If my arrow was coming out in the same direction as I started, then it's positive feedback. Okay? Any other questions? Nope. Okay. So let's do another example. We'll do a bunch of examples for you guys to get comfortable with it. So this was example 2. So we'll start from simple, and then we might make them a little bit more complex. By the way, what kind of feedback is this before I go to the next example? What am I measuring and what am I basically think about it? What am at the input? What am I subtracting? What are the things that I'm subtracting? I'm subtracting a voltage from a voltage, right? And you can see it's in parallel. It's a shunt. I'm sorry, it's series, not shunt. It's series, right? Because this is in series with that. You're adding or subtracting 2 voltages, so it's series. And at the output, what am I measuring? I'm measuring a voltage, sampling the voltage and feeding it back. So I'm basically, it's a series shunt, the same thing as that one. Configuration, if you wanted to, which basically means that the input impedance is going up, the output impedance is going down. We haven't done that yet. We'll do that formally later. And we'll see exactly how to do it in a very simple and elegant fashion. But quantitatively, I mean. OK, so another example. So let's say you have a common source stage. Let's use a bipolar transistor. And so you have feedback here. And then you have an I in. So this time the input is a current. This is R2 and R3. And V out. I think I called them R2 and R3. Yeah. OK. So the question is that, what does this look like? Again, for now, let's draw the small signal model for everyone to just get till we get comfortable without it. So again, emitter is grounded. Use the pi model. So you have an R pi. You have R2 here. GMV pi. And then you have the R3 here. This is V out, and this is V in. So again, and this is I in. First I have to, I'm trying to calculate the asymptotic transfer function, right? So what do we use to scale? What current source we scale? Well, there's only one here, really, a dependent current source. It's this guy. So I can put a k in front of this and say k is going to infinity and see what happens. So if k goes to infinity, I didn't check the sign of feedback again. I forgot again. But this one is easier. So this goes up. This is an inverting stage. This goes down through the resistor. This pushes this down. So the feedback is negative. So it means that, I should have still a finite output when k goes to infinity, which basically means that if there's infinite current that's being pulled here, and the output goes to a finite value, V pi needs to be 0. So it means that V pi is 0, right? Which also implies that this current, called I pi, is 0. Right? Because the voltage is 0 on that resistor. OK, so what do we know now? Again, we are trying to determine what is the relationship between V out and I in this time. So the transfer function is the ratio of a voltage to a current. So it has the units of ohms. Right? It's a transimpedance amplifier call these kind of amplifiers trans resistance or trans impedance amplifier. But we'll talk about that later. Okay, so how do we calculate it? This looks like really bad. So what is the H, what we're trying to calculate? So we're trying to determine H infinity, right? The asymptotic transfer function. Well, H infinity is essentially H when k goes to infinity, which is basically what is H? H is V out over In when k goes to infinity. So when k goes to infinity, I know something simple. This current is 0. Even though I have a resistor here, there is no AC current going through here. So it means that this current, AC, is 0. This is how it becomes simple, right? So if that current is 0, then what can I say about the voltages in different places? What is this voltage, by the way? Also 0, right? So where is this current going? Let's say this current In has to all go through here, right? So what is this voltage? That voltage, this voltage is 0. I know this current is In, so this voltage is simply what? Negative In times R2, right? Because this is 0, this is that much higher. It's Ohm's law. And that's V out. Right? So this is equal to V out. So I know the answer, right? The answer is right there. The answer is negative R2. So to first order, assuming that you have sufficient gain in your circuit, the trans resistance of this circuit is R2. Negative R2, more accurate. That's it. It's very simple, and it's supposed to be. So if I'm designing for a trans resistance of 5 kilo ohms, I'll make that 5 kilo ohms first. As simple as that. Okay, let's do a couple more examples, just to get till you get comfortable with these. Oh, by the way, the type of feedback or the configuration. So what are we adding and subtracting at the input, right? Because if you look at this, this is my I in plus, and this is my I in minus, right? So, and you can see that these two are in parallel. So the input configuration is shunt. And what am I measuring at the output? I'm looking at the voltage, right? So it's a shunt-shunt configuration, if you want to know what kind of feedback it is. Yes? Why did I say I pi is 0? Because V pi is 0, right? Because if we said to get a finite, because we have negative feedback, this is the asymptotic equality principle, right? It says if you have an if you have finite output and you have negative feedback, with k being infinity, the only way you can get finite output when k is infinity is if V pi is 0. To get a finite quantity, when one of them is infinity, the other one has to be 0. So if V pi is 0, then because it's across the resistor, then I has to be 0. And everything collapses to something simple. Okay, any other questions? Okay, so let's do a couple more examples. So this is a slightly different one. I wasn't very economical in the way I used my whiteboards, but it's okay. We'll survive. So here's another transistor configuration. Oh, no, actually, sorry. This is not what I wanted to do. Okay, and the names of these things are R3, R4, R1 and R2, I think. R2 and R1, okay, R1, R2. And this is M1 and M2. So this is V out. And that's I in. So again, we can draw this, let's draw the small signal model for this again, just to be, again, this guy has a source that's grounded, so we'll use the pi model. So it's relatively straightforward if you want to do that. Or we could actually just not do this. Let's not do the small signal model explicitly. Let's just do it implicitly. So in our heads, we know that what's inside here is a GM1 V pi 1 or VGS1. It's called V1. V1. Right? Then what I need to do is I need to scale that by K. So I'm scaling that current source. I'm not scaling GM. I'm just adding this to the value of the current of that particular current source and letting K go to infinity. So what do we get? What happens? If K goes to infinity, what can you say about V1? First of all, again, I forgot to do the most important thing, the sign of the feedback, right? So let's say this node goes up from here to there. Do I flip signs or not? What configuration are we in for this particular because you see, transistor configurations are not fixed. It depends on what you're looking at, which signals, right? For different signals. So from here to there, what kind of configuration do I have? It's a common drain or a source follower. My input is applied to the gate. My output is taken out of the source. So am I inverting or non-inverting from here? Non-inverting. So this goes up too, which is this node, the same node. So this goes up. This pushes this node up. But now, from here to there, what kind of configuration do I have? Inverting, because it's a common source. So I'm inverting, so my feedback is indeed negative. If it was positive, I can't apply this asymptotic quality principle, period. So it's a necessary condition for that. OK, so K goes to infinity. What happens? To get a finite output here, it means that I have to have a finite voltage here. To have a finite voltage with K being infinity, V1 has to be 0. Right? So I know V1 is equal to 0, the voltage here. And when that voltage is 0, this current is 0. Now, it doesn't matter. You may say, oh, OK, well, that current is 0 because the gate of a MOSFET is an open. It doesn't matter. Even if it was a bipolar, that would have been 0. Even at high frequencies, where there's a capacitor there, that's still 0 because the voltage is 0. So this is a much stronger 0 than saying that, oh, it's my gate, it's 0. Okay? So this current is 0. Now that you know this current is 0, what can you say about the circuit? I in has to go through where? All of the I in is going through R1, right? So this is going to be I in. And this voltage is 0. So I know what exactly this voltage is. What is this voltage exactly? Negative I in R1, right? That's this voltage, V2. Right? If I know this voltage exactly, okay, can we determine what the output voltage is? How do we determine what the output voltage is? Well, I need to know what this, what I need to know really is what this current is. If I know this current, then that current times R4 with a minus sign is going to be the output voltage, right? Because there's a direct transfer function from there, 1 to 1. So I need to know that current. Do I know that current? Yeah. It's the sum of these two currents. This current is going to be negative I in R1 over R2. And this current is what? What is this current? Negative I in. So that's the total current here. I shouldn't have written it here. And my red marker is dying anyway. So it's negative I in, that's going this way, and negative I in times R1 divided by R2, which is the current going through here. So which is basically negative I in 1 plus R1 over R2 is that current. So if I ask you what is the V out, what is V out? It's this current being pulled out of R2, so it gives you another minus sign. So you get V out is I in times R4 times 1 plus R1 over R2, and then V out over V in, over I in, sorry, which is the trans resistance, is R4 1 plus R1 over R2. So so this is also what kind of an amplifier. So what are we looking at? At the input, what are we measuring? What are we measuring, or what are we doing? I mean, are we adding currents or voltages? Currents, right? So we are shunt at the input. At the output, though, this time is interesting, right? Because we are really looking at this, we are in series. We are looking at what's the current that's flowing here. So as far as this output is concerned, we are in series. So we are shunt series. Yes? I know what you're going to ask, but okay, go ahead.
Can't you use the same logic for the circuit above? We can see if you're
Yeah, I knew that you're going to ask that. Okay, good question. So he says, let me repose your question. Okay, well, so he's asking this question. He says, how about this? Why couldn't you say that about this guy? Right? It depends on where I'm looking at my output. Here, I am measuring the feedback is connected to where my output is. Right? So this becomes a voltage measurements. It becomes a shunt. Here, my output is not here. Now, if I had drawn this circuit differently, if I had defined a different circuit where my output was here, then that would be a shunt configuration at the output. Now that my output is here, it's a series. And you remember I said this matters only really as far as the output impedances are concerned? And we'll see this later formally and quantitatively. If the output impedance of this node, because from that, if that's the output, this is a series configuration, is going up. The output resistance, if I were taking the output from here, the output resistance of this node is going down. And that's why if your output is here, this is series. If your output is here, this is shunt. And you can say, what if I have both outputs? Well, say, well, you have for one output your shunt, for the other output your series. So it's nothing magical about the circuit. It's like the way zeros depend on where the input and outputs are. The nature of the configuration is also dependent on what kind of inputs and outputs you have. It's a good question. Any other questions? Okay. Let me do one more example. I told you I wasn't economical about this stuff. Okay, now I'm boxed in completely. Okay, let's do it here. So this example is another feedback configuration. We've done how many? 3 transistor examples. So this is one more to give you a sense. And we will reuse these as our canonical examples of feedback networks to see when you go to varying levels of depth into the analysis of what's happening, what you get. So this is the circuit R1, R2, R3, yeah. And M1 and M2. So this is the output. And where do you think the input is? Well, depends on what you're trying to do with it. I'm applying a current source here. So the input is here, the output is there. So you can see without this feedback network, if this was somehow connected to some fixed voltage, right? If I just disconnected it and connect this to some fixed voltage, this becomes a current source, and this is a common gate, right? So it becomes a non-inverting stage from here to there. Now with the feedback, we of course have to check the sign of the feedback. Make sure first that's, so if this is going up, well, this node goes up. This is an inverting stage. This is the common source. This goes down. The non-inverting stage will reflect it out there. So it's negative feedback. And we're trying to find the transfer function for this thing. So again, I need to pick a source to null, not to null, sorry, to take asymptotically to infinity or multiply by k. So what I will do is that we say, okay, well, let's look at this guy. Well, again, the rule of thumb is that its source is not grounded. I use the T model. So if this is IS2, this is IS2. So that's the small signal model for that part of the circuit. This is ground. And then now this is driven by GM1 V whatever 1. And this is where my input current is. I'm drawing only part of, well, I guess I will draw the whole thing in a compressed fashion. So this is the small signal model. The only thing that's left in the small signal model to draw, oh, great. All right, is this part. Sorry, it's a mess right now. This is V1. So this is the small signal model for the circuit. Just drew it on the side. And okay, so let's look at the, again, which one would you pick? I picked this one, the one closest to the input in the forward path. Again, this is a rule of thumb. That's not, I mean, you don't have to. You can do it with any of the sources and it will work still. The whole analysis, the completed. But this one, these usually result in the simplest results. So k going to infinity, if k goes to infinity, right, there, and I have negative feedback, we've already verified that. So to have a finite output, right, what has to happen? IS2 has to be 0, right? So IS2, this has to be 0, which also means that this voltage is 0, because this other side is grounded. There's no current flowing through here, so this voltage is the same as that, which is 0, AC-wise. Yes? It's a V bias, some fixed voltage. So, if it bothers you, when I showed V bias or something that was supposed to look like V bias, that's what I mean. Okay, so what's the V? So we are trying to look at the asymptotic transfer function, right? Asymptotic transfer function, H infinity. So what is H infinity? Well, we know this is V0. So what does that tell you about the current balance here in this node? So it means that the feedback network has to force this current to be exactly to I in, equal to I in. There's no other way for this to happen. The feedback will force this current to be equal to I in, which basically means that, so what we know is that we know I in. So we know I in is equal to GM1 V1. And I know how V1 is related to V out, right? There's a resistive divider, which is, so this is GM R1 over R1 plus R2 V out. So there we have it, right? We have the V out over I in for k going to infinity, which is V out over I in is going to be 1 over GM 1 plus R2 over R1. So this is another transimpedance amplifier, right? Because you look at it at the input. What is the input configuration, shunt or series? You're adding and subtracting currents, right? So it's shunt. What is the output configuration? You're sampling, you're looking at a voltage in parallel. That resistive network is looking at it in parallel. So it's shunt-shunt. In that language, it would be a voltage current, but it's shunt-shunt. And as a shunt-shunt, okay, So that's the asymptotic transfer function. So if I'm saying, okay, I want a trans resistance of 5 kilo ohms. One way to do it is that, well, make this 1 kilo ohm and make this 4, R2 to R1. Right? This ratio, make this 4 kilo ohm, 1 kilo ohm, and make this, if you want it to be whatever, 1 kilo ohm, that's 1 millisiemens. So if you are looking for a trans impedance of 5 kilo ohms, and if you want to use this configuration, you can very quickly arrive at a first pass design. And of course, the assumption here is that if you make this R3 too small, and if you don't, and these are too small, then you don't have gain, then of course, then the correction factors that will come in later will be large. But if the gain is sufficiently large, this is going to be close to what you actually will get, as we'll see. And then we'll see those correction factors later. Okay, any questions? All right.